All right, let us begin. We're going to very briefly go through the answer key for the third exam in Honors Physics. This is the 2A version for class period 2A. To properly draw a free body diagram, we use a dot to represent our object. Then we identify all of the forces acting on that object. We draw those forces using arrows representing vectors in the direction that those forces are oriented. The length of those arrows, those vectors, corresponds to the magnitude of those forces. An object that is in deep space, far away from any planets or stars, means it does not undergo any cognizable force of gravity on the object. So there are no forces acting on the object in deep space as it moves through deep space. Newton's first law tells us that an object in uniform motion remains in uniform motion unless acted upon by a net external force. If there is no net external force, then it would remain in uniform motion. By uniform motion, we mean a constant velocity. All we mean is that uniform motion would change, so there would be a change in velocity if there is an external force. There is no external force here, so the object continues in uniform motion, which is constant velocity. And by that we mean equilibrium, net force is 0. All right, when a car crashes into a wall, your body lunges forward. Your body lunges forward because the car has stopped, because a large force, the force of the wall on the car, has acted on the car, but your body resists the tendency to change its velocity to go from uniform motion to non-uniform motion. That's what we mean by referencing inertia, tendency to resist changes in velocity or changes in motion. That change in motion only occurs when the seatbelt impacts your body or when you finally hit the steering column or whatever you move forward your body. So your body lunges forward because a net force has not acted on you and caused you to change velocity yet. All right, and our fourth short answer is an astronaut floating in space next to his spaceship. As he pushes on the spaceship, he exerts a force on the spaceship. According to Newton's third law, that force that he applies to the spaceship is also applied onto him with the same magnitude but in the opposite direction. So he accelerates to the left, where the spaceship accelerates to the right. They do not accelerate at the same rate because they have different masses. Presumably, they have different masses. However, they do have the same force, magnitude of force exerted on them, according to Newton's third law, just in opposite directions. All right, if you're sitting at a stoplight and you accelerate, your net force must be not 0, must be some value in order to cause the acceleration, and that acceleration is in the same direction as your net force. So the net force is oriented to the right in the same direction as your acceleration. An object's weight on Jupiter differs from that on Earth because the gravitational field is different on Jupiter. Gravitational field on Jupiter is 4 times greater than that of planet Earth. When an object's in terminal velocity, the drag and the weight vectors are equivalent to each other. Therefore, the velocity does not change, so it reaches a terminal or a fastest velocity in which it will not change any further. If an object's moving to the east, the frictional force will be opposing that movement in the opposite direction, which would be west. If an object has a non-zero acceleration, then it must have a non-zero net force that is causing that acceleration. That's what Newton's second law tells us. Also, Newton's first law tells us that. And regarding the frictional force, if you add mass to a system, then its weight increases. But with regard to the frictional force, an increase in the weight would increase the normal force. That's what matters with respect to the frictional force. All right, as Saint Benedict ascends this elevator and goes into heaven, right before he begins ascending, his weight is equivalent to the force that the scale places on Saint Benedict. If it wasn't equivalent, then he would be accelerating, but he's not. He's just standing there, right? He'd be accelerating because there would be some net force. And that's what we see here in this diagram, is that the force of the scale on Saint Benedict is greater than his weight, so there is a net force. That net force is in the same direction of his acceleration, which is upwards at 3.2 meters per second squared. This is the visual of Newton's second law. If we look at the mathematics of Newton's second law applied to Saint Benedict, we see there are 2 forces that are acting on him that we see in our free body diagram. The weight is in the negative direction. The force of the scale on Saint Benedict is in the positive direction. When we solve this equation, we see that his weight and that the force of the scale must be opposing both his weight and causing his acceleration. So mass times acceleration, we plug that into our formula here, and we find that 1,700 newtons of force is what it takes in order to accelerate St. Benedict, who has a mass of 130 kilograms. That's a little heavy for St. Benedict, a little too many of Sunday donuts maybe, at a rate of 3.2 meters per second squared. For St. Michael the Archangel, as he casts the devil, Satan, or Lucifer, into hell, he has two forces acting on him, his weight and the force of drag. That's represented here by Newton's second law, force of drag and the weight. Force of drag opposes his motion, where if he's thrown downwards, then that force of drag must be upwards. The moment after he's thrown, that force of drag is very small because the devil's velocity is small, until some time later, whenever he's falling at a constant velocity because his weight is equivalent to the force of drag acting on the devil, so now he is no longer accelerating. At that moment, those two forces must be equivalent because his acceleration is 0. So we calculate his drag is the same as his weight. His mass, or his weight, depends on his mass in the gravitational field that he's in, which, assuming that the gravitational field of hell is the same as Earth, for whatever reason that might be, we find that it's 900 newtons, but for appropriate significant figures, that would be 2. We'll put 9.0 times 10 to the 2 newtons, 10 to the second newtons. All right, our two blocks that are acting on this system, we have our red block and our blue block. There are two forces that are causing our blocks to move. This is very similar to our Robin Hood problem. Those two forces are the weights of the two blocks that are suspended. We'll consider clockwise rotation. Or this way as positive. I'll actually write that in on my answer key. We'll consider that positive acceleration. Whatever force causes that is a positive force. So the blue block is causing a positive force on the system, and it's opposed by the weight of the red block, which is on the other side of the pulley. Those forces are acting on a system that has a total mass of the mass of the two blocks together, so 3 plus 5, or 8 kilograms. This is how we'd represent the two weights of the blocks, one in the negative direction, one in the positive direction, that's contributing to rotation downwards on the right side of the pulley. And we find that the acceleration of the system is 2.5 meters per second squared downwards, or in the positive direction, or causing clockwise rotation. Okay. In order to find the tension in the rope, we need to analyze one of our two blocks here. Here on the left, I have our red block, our free body diagram for the red block. So we look at our red block, we see tension would be going up. We have the weight of the block going down. That's what we have represented in our free body diagram. Tension up, weight down, that equals the mass of the block that's undergoing these forces times the acceleration of that block. We see that if we resolve and solve this equation for tension, we see that it's mass times acceleration plus mass times gravity. This acceleration is positive, or causing a positive rotation of our system. So we see it's 37 newtons, so this is a positive acceleration. Plug in our values here. Mass of the red block is 3, gravitational constant 9.80 kilograms. 9.80 newtons per kilogram. If we chose the other block, perhaps, the block here, the blue block, in which our tension is pointing upwards and our weight is pointing downwards, we find that it'd be the same tension, 37 newtons and 37 newtons. It doesn't matter which of the two blocks you analyze, you'll see that they are the same. In this case, however, we have the weight and we have the acceleration moving in the same direction as the weight, right? So that's where this negative sign comes in. So it's actually the tension. I'll refrain from saying that. The point being here is that it didn't matter which of the two blocks you analyzed. You find that the tension in the rope is the same on both blocks. All right, moving right along. So now we're in part 3 for forces and kinematics. To find the mass of this block, we just need to go to our weight formula. It depends on the mass and the gravitational field of that block. We find that the block that has 88 newtons on Earth, so we use Earth's gravitational constant of 9.80 newtons per kilogram. We find that the mass of that block is 9.80 kilograms. Forces acting on the block, there's the tension force pulling it to the right, frictional force opposing that tension, and then we have the weight of the block pointing down, and the normal force that's supporting that weight going up. These should be the same length. These should not be the same length because there is some net force. We see that in part C. We see that the net force in the x dimension is the tension minus the frictional force, tension pulling it to the right. Opposing that force is the 12 newtons of frictional force. So our net force is 12 newtons to the right. In the y dimension, we only have two forces. If we look at our free body diagram, we see the normal force and the weight. They're equivalent to each other because our acceleration in the y dimension is 0. It's not moving up or down. It's not changing its velocity in the y dimension. It's constantly 0 in the y dimension. To find the net force, or rather the acceleration in the x dimension, we need to know what is the force acting on what mass. That force divided by the mass of that object gives us the acceleration. The mass of our object we found in 1a, which was 9.0 kilograms, so 12 newtons of the net force in the x dimension divided by 9.0 kilograms. That gives us our acceleration of 1.3 meters per second squared to the right, because that's the same direction as the net force. Lastly, we have a kinematics problem related to this acceleration that's being caused by some net force. We know the amount of time in which this happens, 5.0 seconds. It's from rest, so our initial velocity is 0. We just found the acceleration. The acceleration was 1.3 meters per second squared. We can use our first kinematics equation to relate final velocity, initial velocity, acceleration, and time, and we find that the final velocity of the block is positive 6.5 meters per second to the right, or to the right. All right, Corey Seager's slide into second base. First, we look at kinematics. We see in kinematics that we know the time of his slide takes 1.6 seconds. We know that his final velocity, because he comes to a stop on second base, is 0 meters per second. What we don't know are three kinematics variables. That is how fast he was going at first. We don't know the acceleration he underwent, and we don't know the displacement or the change in position his body underwent as he slid into second base. So we have to resort to some other tools in physics to understand what's happening to Corey Seager. We can't use kinematics to find the length of his slide. We need to go into forces to find some of these kinematics variables, specifically the acceleration. So we'll go into the realm of forces. We'll take a look at forces in the y dimension and in the x dimension. Forces in the y dimension are normal and weight. We have the force of the surface that's acting on Corey Seager, that's pushing up on him, that's opposing his weight. Those two are equal to each other. If the normal force is equal to the weight, we know weight is equal to the mass times gravity. So we can find what the normal force is. Now we can look at the forces that are acting in the x dimension. There's only one force acting in the x dimension, and that is the frictional force, which is opposing his movement on the baseball field, sliding into second base. So I put this minus sign there to indicate negative direction. We know the coefficient of kinetic friction. Kinetic friction, because these two surfaces are sliding past each other. We know the normal force, that's mass times gravity. So we see that mass does not matter whenever we equate these two and try to find the acceleration. We see that the acceleration is negative 4.8 meters per second squared. Now that we have the acceleration, we can return to kinematics. We can relate initial velocity, final velocity, acceleration, and time to each other using the first kinematics equation. We find that his initial velocity must have been 7.7 meters per second. We needed to go through this step 3 because we do not have a kinematics equation that relates time, final velocity, and acceleration and displacement to each other. Those four variables are not found in one kinematics equation, so we had to find initial velocity, find this initial velocity here, after we'd found his acceleration, in order to find finally his displacement. We use a final kinematics equation here, the second kinematics equation, to find the total displacement that his body underwent as he slid into second base. So he slid for 6.2 meters. That is an extremely long slide. All right, moving on. Part 4, vectors. St. Gabriel the Archangel, after completing the Annunciation of the Blessed Virgin Mary, he ascends unto heaven 25 degrees west of north. There's north. To the west of it by 25 degrees would be right there. Our ascent velocity vector would be this vertical component, or the y component of the velocity, and then his velocity along the ground would be the x component of our velocity here. The resultant of those two is his actual velocity, which is 57 meters per second. That's his velocity in 2 dimensions of space. His rate of ascent is his velocity in the y dimension. So I'm going to just draw a triangle here with a hypotenuse that has 57 meters per second as its magnitude. That's from the original velocity. I'll use cosine to relate that hypotenuse to this adjacent side relative to that angle, and solve and find that the ascent velocity is 52 meters per second. If we see that heaven is, that would be 50,000 meters above the ground, or 50 kilometers above the ground, how many minutes does it take St. Gabriel to reach heaven? Well, we just found his ascent velocity. We know that velocity is defined as change in position. In this case, our change in position is in the y dimension, or up and down, over change in time. We rearrange this equation, and we see that the time it took him to travel 50,000 meters at a velocity of 52 meters per second, because that's the rate at which he ascends, takes 960 seconds. We then convert those 960 seconds into minutes, and we find that it takes 16 minutes for St. Gabriel the Archangel to ascend back to heaven following the Annunciation. In order to find the time it took in order to find the distance or change in position along the ground that he traveled in kilometers, we need to find what is his velocity along the ground. We use trigonometry again. This time we're using sine because that is the side, the ground velocity, or the velocity in the x dimension, is opposite this angle. So we need to use 57 sine 25 degrees, which gives us a velocity along the ground of 25 meters per second to the west, more particularly. And then we use his velocity times time to give us displacement, and then divide by our conversion factor of 1,000 meters per kilometer to get to 23 kilometers. Finally, moving to our last problem, we have 3 velocity vectors that correspond to the total displacement of our the golf ball. Due east, then 20 degrees north of east, and then due north. We set up an XY table for each of these putts, putt 1, putt 2, putt 3. When we add those together, we have the resultant displacement in the x dimension, the resultant displacement in the y dimension. The resultant displacement in the x dimension is 6.97 meters when we add all these together, 1.22 meters in the y dimension. You can ignore these I and j components, not to confuse you, that's advanced vector notation. If we find the magnitude if this is how far in the x dimension he traveled, the putt would have gone or went to the right. The distance the putt went north or upwards. We use the Pythagorean theorem and find that 7.1 meters is the total displacement. We know that this putt is over or in the positive direction of 6.97 meters, and it's up 1.22 meters. So the up is our opposite of this angle, whatever angle is right here. There's our angle right there. So we use the arctangent or the inverse tangent of opposite over adjacent, and we find that it's 10 degrees north of east. If you have any questions following this video, please come speak to me. Thank you.